Hello, everyone, and welcome to our webinar on distributed SQL and how it's implemented in CockroachDB. I'm Rob Reid, Technical Evangelist at Cockroach Labs, and by the end of today's webinar, I hope you'll have a good understanding of distributed SQL and its benefits and how CockroachDB fundamentally works at a high level. If you have any questions, as always in our webinars throughout the webinar, just leave us a Q&A comment and I'll be able to respond to it as and when I can. And we'll be sharing out a survey after the webinar to get your feedback. First, before we dive into anything, I'd like to give you a brief history of databases, just to give you an idea as to the genesis of both distributed SQL and CockroachDB. So it started in the 70s, now 55 years ago, with the emergence of SQL itself. And among these databases on this slide are the pioneers of SQL. They're also monolithic databases, having been designed before the age of cloud computing. Now, fast forward a couple of decades, and we have the emergence of distributed data. Among these databases are the progenitors of distributed data. And finally, there are cloud and distributed databases. Cloud databases are essentially the original SQL databases, but in the cloud, and distributed databases are a reimagining of what it means to be a SQL database that's deployed across multiple environments and physical locations. So fast forward to distributed SQL databases, and we have the Spanner white paper that was released by Google in 2012. This was a turning point and a big proponent for the SQL database and what the SQL database could and should be. And it was followed 4 years later by the first distributed SQL database on the market, which was CockroachDB, followed again a year later by Google's own Cloud Spanner. In short, CockroachDB is a database that takes inspiration from all of these database paradigms and combines the strengths of each. Where before you couldn't have both resilience and relational, with CockroachDB for the first time you could. So I've covered the when, but before we cover the what and the how, it makes sense to discover and explore the why. So a database or any piece of software that runs on one machine is a single point of failure. And in the same vein, a cloud database that runs with a single write instance is also a single point of failure. Single points of failure can result in high RPO and RTO, where RPO stands for recovery point objective. That's essentially the amount of time that the amount of data that you'll lose in an outage. That's data that is permanently unrecoverable as a result of an outage. And RTO is recovery time objective, and that simply dictates the amount of time you're spending firefighting trying to get everything back online. It's the amount of time that your application is down. Let's take a look at these in a little bit more detail. This is what RPO looks like and RTO look like in a traditional monolithic active-passive database architecture. So along the, I suppose you could say the x-axis, we have time, and everything up to this point is happy. So we're running happy, we're making backups, and at this point we make our last backup before we encounter an event, an outage. So let's continue on. We're still live, we're still serving customers, but at this point something bad has happened, an outage of some description. Now, this is now data loss. Anything that wasn't backed up before, right up to the point of the event, is permanently lost data. And we're aware of this. Our customers are now aware of the application downtime. And all of this time up to here, and including the expected recovery time, that's RTO. That's the recovery time objective. This is what it looks like in CockroachDB. Now, we've got time along the x-axis still, we're making backups. And at this point, we've made our last backup. And at this point, we have our event. This is our outage, a data center has caught fire, what have you. However, what's different here is, although we are backing up data, as anyone should, it's a very sensible practice, because data is distributed geographically across multiple nodes and replicated multiple times, there's zero data loss. And RTO, the recovery time objective, the amount of time the application is down, is a blip, and it can be measured in milliseconds or seconds at worst. So your database will depend, or your resilience will depend on the database you use and the deployment topology that you employ. So let's take a look at some of those deployment topologies now. While many of our customers replicate data across physical locations, just replicating within the same data center across multiple nodes does yield operational benefits as well. At this level, your database is able to survive software glitches or disk failures or hardware failures of most kinds, and planned maintenance. So if you're planning hardware, if your cloud provider, for example, if you're running in the cloud, is running planned hardware maintenance, or if you're running planned maintenance on the database itself, perhaps, or your application, I would expect there to be zero downtime in this setup. So with this running in this topology, we're in the realm of 3 nines of availability. But what if the building that's housing all of these nodes were to go offline? So this is the primary drawback to monolithic databases. So let's come up a level now. And if our cluster is deployed across physical locations now, maybe 3 regions or 3 availability zones in a cloud provider, or maybe multiple data centers that you run on premise, you're now looking at surviving power failures or wider kind of issues like severe weather events or floods and fires, maybe some network connectivity events that would otherwise bring down the data center itself. This is the realm of 4 nines of availability. But what happens if a whole data center or a cloud region is lost? We come up a level again. Now, this is way beyond the realms of a monolithic traditional database. You need necessarily a distributed SQL database to be able to do anything above running across multiple machines. So region outages are a lot less common than data center outages, but they still go down. In 2023, Europe West 9 in Paris went down, taking down all of the availability zones that were housed within that building because of a flood. Now, at this level, you're surviving very wide systemic problems. These could be very severe. Think of the fires at the moment that are raging in California. These are the kind of events that affect wide populations. The biggest power outage in history affected 600 million people in India. That was 10% of the world's population at the time. So if you're running across multiple regions, however unlikely the event may these might be called black swan events, but they do still happen. So let's go up a level higher. Let's say we're operating in a cloud platform, a cloud service provider, but they go down or they delete your account by mistake. So losing an entire cloud is rare, but there are risks. Cyber attacks or control plane glitches can affect entire cloud service providers. And if you think back to when Google accidentally deleted a $125 billion Australian pension fund, that resulted in an outage for that company that lasted a week. So running across multiple cloud providers, as a number of our customers do, puts you in the realm of 5 nines and above. So let's have a look at the downtime, the impact of downtime now. So it is very common. A stat that I like to reference is Backblaze, the popular cloud storage provider, were replacing a hard drive that had failed for any reason every 30 minutes back in 2023. Now, if your database happened to have been running on one of those failed hard drives, you're looking at data loss and downtime. But they are very, very common. And we spoke with 1,000 businesses last year and gathered stats. And of the professionals that we spoke to, 100% of their businesses experienced outages that affected their net income across the year. And of all the people we spoke to, on average, each business on average encountered 86 outages across the year, with some encountering outages, I think it was about 14% every day. So these are very, very common. And they're getting more expensive. For a small business, we're looking at around $25,000 per hour of lost income. And that's not including the reputational damage that comes alongside these outages. For a large business, we're over $500,000 per hour. And for the largest businesses, it can be in the many millions of dollars per hour of downtime. And that's only getting worse. So what I look at here, what strikes me as interesting with these costs is actually the outages may be costing your businesses more than you're spending on the technology that could be used to prevent them. There's a link here if you'd like to scan it, if you haven't already, that takes you to our freely downloadable report that is the state of resilience in 2025. So onto distributed SQL now. Let's look at the tenets of distributed SQL. First, we have consistency. The data that you put into your database must match the data you get out, whether that is a monolithic database or a distributed database. But we're talking about distributed databases here. So regardless of the node you speak to, any other node, if it provides strong consistency, should give you exactly the result that you're expecting. And it seems almost too obvious to mention, but if that's not the case, money is going missing, medical records are incorrect, or audits are being failed. And this is the world, if not met, of eventual consistency. And it's not something that you might want to run for a system of record that needs to be exactly up to date all of the time. Next, we have resilience. If a portion of your database infrastructure becomes unavailable, the database as a whole must remain online with no data loss and no loss of data integrity or consistency. And the database should also be natively geo-distributed. If your database won't survive a data center or regional outage, it can't do that unless it's running somewhere else. So unless your data is geographically distributed, you'll have to manage separate databases to meet different customers where they are, which comes with costly maintenance burdens. From a single distributed database, you can meet all of your customers wherever they happen to be in the world from one place, lowering the total cost of ownership, lowering the amount of maintenance you're having to do. And finally, the database should be easy to scale. Scaling your database should be a non-event. It shouldn't mean taking your business offline, whether you're scaling up or down. So being able to treat your database as you would any other piece of your infrastructure means you're not tied to expensive hardware. You have flexibility to move between hardware, and it allows you to move between data centers and cloud providers, which gives you a lot of flexibility and lowers your cloud concentration risk. So let's now dive into CockroachDB itself. I'll start with the fundamentals. So this is the smallest form of compute in CockroachDB is the node. And it could be a running binary, it could be a Docker container, it could be a Kubernetes pod, but the node is the smallest level of compute in CockroachDB. And this is where the monolithic database finishes. It's one node and that's where it stops. Going up a level higher, we have the cluster, and a cluster is a group of nodes that work together to balance and rebalance data and to provide read and write capacity for customers, old and new, as they come online. A node can be given a locality, and these localities give Cockroach an understanding of where to place your data for optimal query and data placement and performance, but also data residency. If, for example, you need to be able to pin your data to specific locations for regulatory compliance, localities are how you achieve that. And then we have ranges. A range is simply a contiguous block or chunk of table data, which by default is half a gigabyte in size, around 512 megabytes. And the table is transparently split into these ranges. This is not something that you have to think about or manage. And we call this range partitioning. So as a result of this, you don't need to shard anything manually. Scaling your cluster up or down is a non-event. CockroachDB, as a result, doesn't need a master or primary node. And you can satisfy customer demand however large it gets. Next, we have replicas. A replica is simply a copy of a range, and it's expressed by the replication factor in CockroachDB, which for a single region cluster is 3. So there are 3 copies of your data, and 5 for a multi-region cluster, although it's completely up to you what you set your replication factor to. But we recommend at least 3 in order to survive the outage of one node. So in this example, range 1, which has this data, has 1 replica, and altogether there are 3 replicas for this data, all containing the same data. And those replicas exist on different nodes. That's how CockroachDB is able to remain online in the event of a disaster. It's because your data is safe. So this is range 1. It's replicated 3 times across 3 different nodes. That's range 2, also replicated 3 times. And finally, range 3, replicated 3 times. There could be any number of ranges on your data. It depends on how much data you have and how large your ranges are, which is configurable. And each of these ranges is given, so one of each replica range is given a leaseholder. So that's not nominated to be the leaseholder. So for range 1, replica 2 is the leaseholder. For range 2, replica 3 is the leaseholder. And for range 3, replica 1 is the leaseholder. That's a tongue twister. This is what controls reads and writes to a given range of data. And it allows CockroachDB to remain strongly consistent, even though data is geographically distributed across the nodes. So you might be wondering how this all comes together and works. So let's look at a read operation and a write operation now. So we have a client up here, and they're connecting to CockroachDB via a software or hardware load balancer. Their request hits a node, and the first node that it hits, because of the routing of the load balancer, we call the gateway node. Every node is capable of becoming the gateway node. It just happens to be the node that is hit after the load balancer. The gateway node knows where the data is, and that's because of the system meta ranges, which instruct all of the nodes where to find all of the data. So it knows that it needs to speak to, for an authoritative answer. You can ask for slightly stale data, a non-authoritative query, but for an authoritative consistent query, that query is routed to the leaseholder, which knows exactly what the data should be at exactly that moment in time. The data is returned to the gateway node, which in turn responds to the caller. A write is quite similar. The client connects to CockroachDB via the load balancer. I've chosen node 3 again for no other reason. It could have been any of these. And then the gateway node communicates with the leaseholder, sending that write intention. And the leaseholder then orchestrates the write to its follower replica, the other replicas that don't happen to be leaseholders for that range. The first one to respond in a replication factor of 3 cluster, the leaseholder now knows that that data is safe because it's replicated at least twice at this point. So it can respond to the gateway node, which in turn responds to the caller. Asynchronously, the other replica, which may have been maybe geographically further away, and so the speed of light has slowed that request down, also lets the leaseholder know that data has been safely committed. So let's talk about rebalancing replicas here. In a 4-node cluster, let's say we want to add a node to the cluster. So there's our new node. Now, each of the nodes is aware whether it could accept more data or perhaps has too much data and would like to offload some of it. And that's still orchestrated by the leaseholders. So the leaseholders are these ones here, colored in gray instead of white borders. So we've added a node to the cluster, and we know through the consistency of the cluster that now this node can accept more data, and all of the other nodes in the cluster have 2 replicas or 2 ranges. So that's all that was required in this instance. Let's say we temporarily lose a node. In this instance, there aren't any leaseholders on this particular node. So what happens is the node goes down. If it's down for less than 5 minutes by default, we call that time until node dead. When it comes back online, the leaseholders simply replay any transactions that happened back to that node, and we call that up replication. So they're bringing that node back up to date. If, however, we permanently lose a node and it's down for more than 5 minutes, and that's a configurable window. In this case, we've lost a leaseholder. We assign a new leaseholder. So you can see that this one's just become a leaseholder. I'll do that animation again so you can see. So that's just become the leaseholder. And now we know that we've got under-replicated data, so we need to create new replicas. So there's a new replica of the blue range here and a new replica of the pink range here. And eventually, when a node comes back online to replace node 3, the same process will happen again. The nodes will realize that node 1 perhaps might have a bit too much data and is in an imbalanced state with the other nodes, and it can offload some of that to the new node. So in a distributed database, it's not enough to simply distribute the data. The execution of SQL queries themselves needs to be distributed in order to make the most of the challenges around the speed of light, and in order to make the most of network bandwidth transfer and satisfying customer demand. With any distributed SQL, with any distributed system at all, network latency becomes an important consideration. You can't beat the speed of light. So to make each query as efficient as possible, CockroachDB pushes the SQL execution to where the data is located. I'm just received a question here. How is it different from any monolith database to say Oracle, sharded across multiple geographic regions and multiple read replicas? Okay, let me just digest the question. So how is it different from any monolith database sharded across multiple geographic locations and multiple read replicas? So I'm guessing in the case of Oracle, as is the case with most cloud databases, there will be one source of truth for writes. And I myself have manually sharded a Postgres database, and it necessitated that I was using foreign data wrappers, and it's necessitated that I have one node to control writes. If not, I could get into an inconsistent state with my data, and it all became a bit of a nightmare. And that's just for one table. So you'll face different challenges whether you're using Oracle or a distributed SQL database. With multiple read replicas, the data will be asynchronously transferred to those read replicas. But in this particular context, you're not distributing the SQL execution. These are read replicas. They're not smaller chunks of data. So for example, in this diagram here, it might be that West Coast customer data exists here, European customer data exists here, physically pinned, and East Coast customer data is here. You don't need to configure that beyond a single line in your table create statement to say, this is a regional by row table, and I want to position data based on a column. By default, that's called CRDB region. So what we'd need to do here, if let's say we have a product table that spans 3 regions and we're looking for the top 10 most sold products, the query will start 3 processes, one for each of the regions where the data exists. And CockroachDB, because of its distributed nature, it knows where data can be physically located. So it knows, in this case, we're looking for all products around the world. It needs to start 3 processes, one for each of the regions. So the aggregations are performed where the data lives, and that simply reduces the amount of data that's being sent across the network, enhancing the usability and performance of the database. And then finally, there's a final aggregation step that's performed with any grouping or aggregations that are required by the gateway node before the data is returned to the caller. So we're sending a smaller amount of data around across the cluster, and then yet a smaller amount of data back to the caller. And this goes right back to our cost-based optimizer, which itself is distributed and geographically aware. It will generate a number of queries or different query plans for any given query, and it will execute the one that's deemed to have the lowest estimated cost. And in this very simplified diagram, we've got a multiple write transaction. And this is what it might look like in a typical distributed system. So a transaction comes in and is set to pending before it gets a response. So everything's linear and done in serial. And then we start to send the data for commit. We send the data, we get a response, we send the next row, we get a response. From a time perspective, that's very inefficient and generally time consuming. So instead, CockroachDB can perform multiple actions in parallel. We call that pipelined parallel execution, which lowers the execution time and increases the throughput. So instead of sending everything in serial, we send everything in parallel, and we can commit everything at the same time, shaving off about half of the amount of time. And for those of you aware of DORA, or those affected by DORA, perhaps you're in financial services, you might be realizing that distributed SQL might not only be good for application availability, but also to mitigate your cloud concentration risk. If you can run a database that's completely cloud agnostic, you can run it anywhere. You can run it on your on-prem infrastructure, and you can run it across clouds. We have customers who are asked to demonstrate their ability to survive cloud outages. And by doing that, the auditors will say, turn off this cloud and survive the outage. And they do, and they manage to survive the outage. So a happy side effect of a smarter database is a simplified architecture. So let's have a quick look at architectural simplification. There is a fantastic custom video from a company called Spreedly, who talk about their journey from a number of different databases that were hyper specialized for different tasks, and a lot of code that was used to bring everything together into CockroachDB. So things like horizontal scalability, geo-partitioning, built-in change data capture, they all contribute to a simplified architecture. And in some instances, companies are realizing that they can not only simplify their architecture, but their engineering organizations as a whole. Next, we have use cases. There are a lot of use cases that benefit from a distributed SQL database. This list is by no means exhaustive, but we have a playlist as well on YouTube that explores some of the most used, most frequent use cases that we encounter. I'll let you take a quick snap of that. Okay, and finally, I'd like to talk about TCO, total cost of ownership, because I think you'd be forgiven for thinking that a distributed database would be more expensive than a monolithic database, and that doesn't have to be the case. Let's assume we have a workload that requires around 10 CPUs and around 40 gigabytes of RAM. In a primary standby configuration, each node must be able to support 100% of the production workload. So that's 100% of the production workload for the primary while everything is going happily, and 100% on the standby, just in case we need to fail over to the standby. And that means that at any given time, around 50% of the infrastructure, depending on how the standby is being used, is sat idle. So let's take a look at some specs. To satisfy this workload, and this is just AWS, this could be a cloud provider or your own on-prem environments, we're going to need two M6A4X large machines to cope with this workload. One machine offers 16 vCPUs and 64 gigabytes of RAM, which is more than enough to satisfy our workload with a bit of headroom. But together we're looking at 32 vCPUs and 128 gigabytes of total RAM. That costs around, as of a calculation I did this morning, just over $1,000 per month. And it gives you a headroom of 6 vCPUs because you're only looking at the headroom against one machine, and 24 gigabytes of RAM. Contrast that to a distributed SQL database, and things look quite different. Every node contributes to the whole production workload. So we're not looking at having a node dedicated to 100% of the workload. We're looking at having multiple nodes that contribute a percentage to the overall workload. And at no point is any of this infrastructure sat idle. So let's take a look at some of these specs. In this, we're using more machines, but they're smaller machines. So instead of 2 M6A4X large, we're looking at 3 M6A2X large. Now, obviously, your choice of machine is very much up to you, but this is just indicative. Each machine has 8 CPUs and 32 gigabytes of RAM, which in itself is not enough to satisfy the total workload, but together they sport 24 vCPUs, that's a typo, and 96 gigabytes of total RAM. And that will cost around $756 per month. And that's just a non-reserved instance, non-demand instance. And that will give you 14 CPUs of headroom and 56 gigabytes of headroom in terms of RAM. So essentially you're getting more bang for less buck and greater resilience at the same time. Now, we've reached the end of the webinar, the structured webinar. There'll be time for Q&A at the end. I'd like to just leave you with distributed SQL can be operationally very simple to run. You don't need to understand distributed SQL databases deeply in order to be effective with them. I've deployed databases by manual sharding and via CockroachDB. And from my own experience, of which there are videos on YouTube where you can see me pulling my hair out, it is a lot simpler to deploy a distributed database than it is to deploy disparate instances of the same monolithic database. And the distributed SQL paradigm is a necessary evolvement of the database against today's modern workloads and operating environments. We're looking at things like GDPR and DORA, CCPA, etc. It's a requirement now as we go into the 2025. A distributed SQL database is probably a sensible choice for your business. And as we've just seen, it can be more efficient than running separate instances of, or active passive disaster recovery mode monolithic databases. So with that, I'd like to thank you. I'm just going to go through the Q&A now, and I'll try to address your questions. Okay, so we have a question. Can't we achieve the same thing using HDFS with MR working on cloud with load balancing and backup provided by the cloud service provider? HDFS, is that high density file system? If I'm completely honest with you, I don't think I'd be able to give, someone's just got back, the Hadoop framework. Thank you for that. Thank you. I honestly don't know Hadoop well enough to give you an authoritative answer on that. But if you'd like to, I can do some digging and get back to you once the video is uploaded on YouTube. Leave a comment on the YouTube video once it's uploaded, and I can get back to you on that. But apologies, I'm not able to answer that right now. Is writing data to all replicas synchronous in CockroachDB? So yes and no. In order to commit the data, so we know it's safe, you'll need to get a response from one of the replicas. The other replica, once we've got a consensus or quorum of data, so in a replication factor of 3, that is 2 nodes need to agree on the data to achieve quorum, we can return straight back to the caller. We don't need to speak to all of the nodes in order to gain quorum and return to the caller. So yes and no. CockroachDB will hear back from its closest replica. So the leaseholder will hear back from the closest replica. So for example, if you're running a single cluster across the states and you've got nodes in the middle of America and the west and east coast of America, if one happens to respond slightly quicker than the other, that will be your total round trip time for that request. A common misconception with CockroachDB and probably distributed SQL databases in general is, if I have a cluster of 100 nodes, are there 100 replicas? And the answer is no. The number of nodes and the replication factor aren't always the same. In a cluster of 3 nodes, the replication factor will be 3, and they are the same. In a cluster of 5 nodes, if you have a replication factor of 3, there will be 2 nodes that don't have knowledge of a particular range, or at least they don't physically store the data. They'll still have the knowledge of it. What is our migration process from Oracle? So if you want to migrate from Oracle, which a lot of our customers have done, you're looking at a couple of steps. So first, we have the schema conversion tool, which is part of our MALT, or migrate off legacy technologies framework. And that will allow you to convert your Oracle schema into something that is digestible by CockroachDB. And that might be converting tables, columns, data types, and things like that into something that CockroachDB can understand. It will also send errors if it encounters a table that it can't translate, or there's not a one-to-one mapping that it can achieve. And it will translate things like triggers, store procedures, and functions where it can. It will let you know if it can't translate something. So that will all come into the considerations that you need to make. But then you're looking at the process of migrating data. We do have a tool called Malt Fetch for that, which is soon to have support for Oracle, if not already. So you'll be able to stream data from your Oracle database into CockroachDB. But there are a bunch of off-the-shelf tools that are available for this as well. I think Click Replicate, Stream, STRIIM, and Amazon DMS, Data Migration Service, can all do something similar. So the choice of tools really depends on your requirements. So I think that's it for now, unless there are any other comments. Let's have a quick, just to scroll through. Oh, sorry, we do have a question. Yugabyte is another offering in the distributed SQL space, but I understand they use a different approach to the storage layer, not a key value store like CockroachDB. Why is Cockroach better than Yugabyte? Now, obviously, this is going to be a very contentious question, and I would urge you to do your own testing, of course, when it comes to any system. But some of the differences are Yugabyte's use of hash partitioning as opposed to range partitioning. We have a blog post that talks about the differences there. But I would urge you to try them and see which one works best for your workloads. And if there are no more questions, which I don't think there are, I'd like to thank you all very much for attending. It's great to see so many of you on the call. You'll be sent a survey, as mentioned. Please let us know what you thought, what we can improve for the next webinar. But otherwise, have a lovely rest of your day and evening. Thank you.